Hi, I am Parsha and I am currently pursuing AI machine learning and data science at Red and White Scale Education. For this project, I was given the role of junior data analyst at an educational research institute, and the task was to build something called expectation decider, a model that looks at historic data of students and works out the probability of a student passing a competitive math exam based on the things like their study hours, attendance, participation in group discussion, and their previous test scores. In the next few minutes, I'll walk you through my full notebook, how I generated the dataset to how I solved every part of this assignment, from basics of the probability all the way to Bayes' theorem. Now, let me share my screen. So, this is my notebook in Google Colab. Here is the list of topics that I have covered in this file. I started by generating a dataset of 200 students with NumPy and pandas, where the information like student study hours, attendance, group discussion participation, previous test scores, and final results are there. I have deliberately set it up to 60% pass and 40% fail, where the students who attend more and study more are more being likely to pass, just like in real life. I have also saved this as a CSV file. Moving to question number 1, I started with the basic definition. Probability is just the likelihood of an event, which is calculated as total outcomes over favorable outcomes, and it always lies between 0 and 1. As an example, I quickly calculated that a probability of a student selected randomly is passing the exam. So the answer comes to 0.6, and we can change it into percentage. That comes to 60%. Next, I map the standard probability vocabulary to this exact dataset. Experiment is picking one student's actual record. Sample space is all 200 students. An event is like condition, passed the exam. An outcome is one student's actual result, and the random variable is a number attached to a random pick. So it's not abstract theory, it's tied to something concrete. Like here we can see the whole code of this. Then to finish question 1, I calculated 3 separate probability events from this dataset. For example, probability of a random student has attendance greater than 80%, which came to 0.48. So we can say 48% of students has greater attendance than 80%. Moving forward, probability of a random student studies more than 10 hours a week. So it comes to 0.565. So we can say that 56% of students studies 10 hours a week. And then probability of a student participated in group discussion. So it comes to 0.5. So I deliberately make the data set like this. So it has came like exactly half of the students from all 200 sample space, they have participated in the group discussion. So for question number 2, I compared two types of probability for the same event, a student passing. Like theoretical probability assumes no data at all. So if pass and fail were equally likely, that would be 50%. Here we can see. This is the formula or the code for theoretical probability. Whereas empirical probability actually counts what happens in my 200 real records, and that comes out to 60%. Here we can see if we apply empirical probability formula, we can get 60% student has passed. So the 10-point gap is whole point of this section. Real data beats a blind assumption. So question 3 asks for a random variable. So I define x as the number of students who pass out of three randomly selected students from the dataset. Since 3 is small as compared to 200, I treat this as binomial, where the n is equals to 3 and p is equals to 0.6, and calculate each probability by hand for x is equal to 0, 1 and 3, checking this sum to exactly 1. I also plot this as a bar chart, and we can clearly see that x is equals to 2 is most likely outcome. Then I calculated mean, which is 1.8, meaning about 2 out of 3 students are expected to pass, and the variance, which is 0.72, both 0.72 both cross-checked against the shortcut formula, and they matched exactly the same. So for question 4, I need Venn diagram of two groups. Group A, students who study more than 10 hours a week, and Group B, students who attend more than 80% of classes. So I count each region separately, where I found 113 students are the students who study 10 hours per week. 96 students are the students who has 80% greater than 80% attendance, and 80 students who 80 students are the students who satisfy both, which I draw using Matplotlib underscore Venn library, which I draw using the Matplotlib underscore Venn library. I then double check everything using the additional rule of probability, which confirms about 129 students. 129 students, nearly 65%, fall into at least one of these two groups. So question 5 needs a contingency table. So I cross-tabulate group discussion against final result by using pandas cross-tab. It immediately shows 80 students who did a group discussion passed against only 40 who didn't. From this, I calculated joint probability of doing a group discussion and passing, which is 0.4. The marginal probability of just passing, which is 0.6, and the conditional probability of passing given a group discussion, which jumps to 0.8. Everything is coded here. You can see it's well commented and easy to understand for anyone who sees this file for the first time. So the jump from 60% to 80% is a big clue. So in question 6, I formally test independence. If a group discussion and passing were independent, P of yes times P of pass should equal P of yes and pass. 0.5 times 0.6 gives 0.3, but the actual joint probability is 0.4. So they are not independent, they are dependent, and since students can satisfy both at once, they are not mutually exclusive either. So question 7 needs Bayes theorem. Using its own separate number straight from the assignment brief, 70% of students who passed has high attendance, 40% of students who failed also had high attendance, and 60% of students who had high attendance, 60% of all students had high attendance. I first used the law of total probability to work backward to a baseline P of pass of about 66.7%. Then plug that into Bayes theorem's formula to get P of pass given high attendance, which comes to about 77.8%. So high attendance generally pushes up the probability of a student getting passed. So finally, I bring everything together in a summary, comparing all 4 factors like attendance, study hours, previous test scores, and group discussion by how much they shift the probability of passing. Attendance and study hours turn out to be the strongest factor. Students above the threshold of either one pass more than 90% of the time, compared to under 30% for those below it. Group discussion helps too, but it's the weakest of the 4. So the biggest takeaway from this whole project is that consistent attendance and regular study hours matters more than anything else for passing this exam. So this is the complete expectation decider project. Starting from a synthetic dataset of 200 students through basic probability, empirical versus theoretical probability, a random variable with its full distribution, a Venn diagram, a contingency table with joint, marginal, and conditional probabilities and independence tests, and finally the Bayes theorem, all tied together with a data-driven conclusion about what actually predicts whether a student passes. This has been my submission for the Expectation Decider project under Red and White Skill Education. Thank you so much for watching, and I hope this walkthrough made the logic behind every step clear. That's it from my side. See you in the next one.